Welcome to This Explainer. If you've ever stopped and wondered how a sleek, brand new gaming laptop and a clunky 10-year-old desktop can both run the exact same version of Windows perfectly, well, you're in exactly the right place. Today, we're definitively untangling two of the most commonly confused terms in computer science: computer architecture and computer organization. We're going to unscramble the matrix to really separate the logical blueprint of a machine from the physical bricks used to build it.
Look, to understand why this matters, we kind of have to acknowledge the core confusion first. As William Stallings notes in our source text, these terms are frequently swapped, even by seasoned professionals. He points out that people use instruction set architecture interchangeably with computer architecture, while organization is relegated to just the physical nuts and bolts. Even foundational textbooks point out how frequently and incorrectly these terms are treated as synonyms every single day. But under the hood, they represent two fundamentally different sides of computer design, and confusing them means missing out on the brilliant engineering that makes modern tech possible.
Okay, so here's our roadmap for today. We're going to start by defining architecture, then organization, compare them side by side, explore the processor family in the real world, bridge the hardware-software gap, and finally, trace the evolution of architecture itself. Let's dive right in. Section 1, Defining Architecture, the Programmer's Blueprint.
So what actually is computer architecture? Basically, it refers to the attributes of a system that are strictly visible to a programmer or a compiler writer that have a direct impact on the logical execution of a program. Think of it like the rules of a board game. The architecture dictates how many spaces you can move, what the cards do, and how you actually win. You don't really need to know what factory printed the cardboard or poured the plastic game pieces to play the game, right? You just need to know the logical rules. Well, in computing, architecture defines the exact instruction formats, the opcodes, the number of bits used to represent data types like integers or characters, and the memory addressing techniques. If you're writing software, the architecture is the unchangeable set of rules you absolutely must follow to ensure your program runs correctly. It is the absolute what of the system.
Moving on to Section 2, Defining Organization, the Physical Implementation. Now, computer organization, that's an entirely different beast, mainly because it's completely transparent to the programmer. It refers to the operational units and their interconnections that actually realize those architectural specifications we just talked about. If architecture is the what, organization is the how. A programmer relies on a multiplication command working flawlessly. They honestly don't care if the hardware engineer achieved that by using a dedicated, super expensive hardware multiplier chip or a cheaper, slower series of repeated additions. That's the engineer's organizational problem. Organization is all about the physical hardware details, the specific control signals, the interfaces between the computer and peripherals, and the underlying memory technology being used to make the blueprint a reality.
Let's ground this in reality for a second to understand this organizational hierarchy in a traditional computer structure. At the top, we've got the central processing unit, or CPU, which acts as the brain of the operation, crunching all the data. Then we have main memory, which you probably know as your RAM, holding the immediate data you're working with. Next is I/O, or input-output mechanisms, so things like your keyboard or monitor. And finally, the system interconnection, typically buses, which act as the physical highways carrying data and control signals between the CPU, memory, and I/O. When you're reading the spec sheet of a new computer at the store, you're largely just reading a list of its organizational components.
Section 3, Architecture versus Organization, a side-by-side look. Let's actually put them head-to-head. On the left side, we have architecture, instruction sets, addressing modes, and high-level I/O mechanisms. On the right side, we have organization, the generation of control signals, the choice between SRAM or DRAM memory technology, and physical hardware multipliers. And here is the ultimate takeaway, the economic and practical why behind this entire separation. If you change the architecture on the left, you break the software. Old programs simply won't know how to run, and rewriting them costs literally billions of dollars. But if you keep the architecture the exact same and only upgrade the organization on the right, like swapping in faster memory or a more efficient logic gate, that exact same software still runs. It just runs incredibly faster. This vital separation is literally what allows the tech industry to progress and sell you faster computers without having to reinvent the wheel and rewrite every piece of software on Earth every single year. Section 4, the processor family. Same blueprint, different bricks. Think about the Intel x86 processor family for a moment. A piece of software written for an x86 processor back in the late 1990s can, astonishingly, still execute perfectly on a top-of-the-line modern x86 chip today. Why? Because they share the exact same architectural blueprint, they speak the same logical language, but the physical organization, the arrangement of the transistors, the cache sizes, the incredibly tiny nanometer scale of the actual silicon is light years ahead of where it was in the 90s. The processor family concept works because manufacturers fiercely protect the architecture for backward compatibility, while constantly and radically changing the physical organization to boost speed and lower costs. It's the same blueprint, but completely different physical bricks.
Section 5, the hardware-software interface, bridging the semantic gap.
So, our sources describe this fascinating concept called the semantic gap. It's basically the huge, daunting difference between the abstract operations provided in high-level programming languages and the raw physical realities of computer hardware. To bridge this gap, we use the Instruction Set Architecture, or ISA. The ISA isn't just an interface, it's a strict treaty between the software developers who write the code and the hardware engineers who build the silicon. It defines the exact vocabulary the hardware understands. Without defining the ISA first, you simply cannot initiate the design of either the hardware or the software.
I absolutely love this visual metaphor taken directly from our source material. Check this out. We have stick figures up top representing software programs, just running around and happily executing their tasks. They're standing firmly on a platform labeled Instruction Set. Now, notice the grimacing hardware stick figure at the bottom, doing all the heavy lifting to physically support that instruction set bridge. It's so perfect. The ISA provides a stable, clean, and predictable platform for the software to dance around on, while completely hiding the incredibly complex, sweaty electrical work happening in the physical hardware underneath. The hardware sweats so your software doesn't have to.
Section 6, Evolution of Architecture, a shifting focus. Now, if we rewind back to the origins, like John von Neumann's stored program computer in the 1940s, the very definition of architecture has continuously shifted. Why did this happen? Well, in the 1950s and 60s, just making a machine do complex math without breaking was practically a miracle, so the entire focus was on computer arithmetic. By the 1970s and 80s, as human programmers gave way to automated compilers, we desperately needed smarter, more efficient instruction sets to handle all that complex code. But fast forward to the 1990s and today, processors have become so unbelievably fast that memory simply cannot keep up. It's a real bottleneck. So the entire industry is now obsessively focused on memory system hierarchy, CPU design, and multi-core processors just to feed the beast and keep the CPU busy. So balancing this entire computer system really comes down to the three pillars of computer architecture: hardware, software, and the instruction set. The hardware provides the raw physical power. The software provides the logical instructions, and the instruction set acts as the essential interface binding them both together. Mastering the difference between the architectural blueprint and the organizational hardware isn't just semantics. It is the absolute foundation that allows our digital world to rapidly evolve, get faster, and become cheaper, all while remaining miraculously backward compatible. I want to leave you with this provocative thought. As we push the physical limits of silicon and enter the era of dedicated AI accelerators and quantum computing, what will the computer architecture of tomorrow look like? Will our fundamental logical blueprints survive, or are we going to have to tear them up entirely to accommodate the wild new ways we're organizing physical matter? Thank you so much for exploring this with us, and keep questioning how our digital world is built.